So some people like to call this the sum rule because it's involving sums. But let me write out what that means. That was a little bit of a fun slant there. So if f is big O of h, so remember we're having another one of these conditional statements. So it means that we're going to have this and the following also satisfied, and g is big O of h, then it has to be that if both of those are true, then it has to be that f plus g is big O of h. So suppose I give you three arbitrary complexity functions, f, g, and h. If f is big O of h and g is big O of h, then you could say that the sum of f and g must also be big O of h. So you might say, Dan, we've seen a statement sort of like this before, but not entirely. It's now got two conditions here like this. So how can we use that? Well, let's first write down the game plan so we know the ultimate strategy for what we're going to do here. So that's usually a good place to start. So we understand the statement. Also, it's a good idea your reader has some idea what you're doing. To prove the claim, remember these are three arbitrary complexity functions. So I'm just going to avoid writing that here just because it just adds space here that we don't need to use. But if you find yourself really needing to see that, or say you need to write that out every time you're used to it, just do it. We determine constants. Right? We need to find those two constants, or we're going to find those two constants for the big O definition. C, which is a positive real number, and we have n0, which is a positive integer. Right? Such that the following is the case, such that for all n greater or equal to n0, it has to be that f of n is less than or equal to c times. Now, are we trying to prove c times g of n, or are we we're trying to prove that f? So remember, we need to make sure we state clearly what we're actually trying to do. So it's very easy to fall into the trap of just writing out like what you're used to writing every single time for the big O definition. But remember, the claim isn't that. The claim is if we have those two things, then f of n plus g of n is less than or equal to c times h of n. That's what we're trying to prove given these two things. So you might say, Dan, what are you going to do here? Now, in a previous claim like this, like where we had some condition we can use, we would like to be able to invoke something here. Well, we have if f is big O of h and g is big O of h. We know both of those are big O of h, right? Well, let's just pull out their definitions, right? We're going to use existential instantiation to create names for those constants that exist for each one of these big O definition applications. So we're going to apply the definition of big O here. We're going to apply the definition of big O right here. And then we're going to kind of take them, give those constants names. Then we're going to try using them, okay? So both f is big O of h and g is big O of h, implying the following, right? Implying we have pairs of constants. I'm just going to list them all out together, and then I'll write out two inequalities for each. Well, one inequality for each, sorry. Implying there are constants. There are constants, C1 and C2, which they're going to be positive real constants, and N1, N2, which are going to be positive integers. So that the following is the case. So that f of n is less than or equal to c1 times h of n for all n greater or equal to n1. So far we have that, right? That's the first application right here, right? That's f is big O of h. This is what this says, is that we have c1 and n1 in relation to this inequality. F of n is less or equal to c1 times h of n. And now we have the other one. And g of n is less than or equal to c2 times h of n for all n greater or equal to n2, right? We have both of these at our disposal. So for sufficiently large values of integers, right, we have n1 and n2. For n1, you know that f of n is less than or equal to c1 times h of n, right? And we also know that for values n2 and greater, that g of n is less than or equal to c2 times h of n, right? So the intuition behind the sum rule is that, suppose I take a function, I don't know, let me just, gotta get it out of here. It takes a lot of force. Let's get it out of here. There we go. Now let's get this one open too. So I have two, suppose that these are two arbitrary complexity functions, f and g. So what the goal in our proof will be is, suppose that this is f and that's g. If I take these together, and suppose that this set over here, this bucket, is big O of h, it should be that if one of them is in big O of h and the other one is big O of h, it has to be that when I add them together, whatever the contents of these are, they should both together be able to, like if I took these, take a piece of let me just get some tape here. Let me just go grab that. So suppose that I have these, suppose I have f and g. So if I sum both of them, if I sum up both of them, it should be that when I take them together, each one individually, actually, I think it needs more tape. I think it needs more tape. Let's get some more tape on here. Let's get some more tape on here. Let's get some more on here. Okay, there we go. Definitely, now it's not going to move anywhere. So I have f and g, I've summed them together. The intuition about this statement is that it should be that when I sum the two together, they also should go into big O of h, regardless of what they are inside these magic boxes. So this one would just be f, this is g, or this is g, this is f. The point is that when I take them and sum them together, they better belong to the same set of complexity functions. So now I have these two inequalities. I'm going to employ something you should remind you of the max rule when we did that approach. Now I have two inequalities, but here's the thing. I know that they're true for only certain values of n1 and n2 and up. So I need to make sure that when I state this next part, I make sure that I state it for n that are sufficiently large. So I need to actually say what values those are. So this is actually how you might phrase this bucketing approach that we've been using. This is one way you can phrase something like this. By summing over both the inequalities. If you find yourself not satisfied with that description, you can always give names to the inequalities. Over both the inequalities. When n is greater or equal to the max of n1 and n2. So it's important that we have it where it's going to be at least n1, n2, right? Because remember, that first inequality was true for n is greater or equal to n1. The other one is true for n is greater or equal to n2, right? So if I make sure it's at least as big as the larger of the two, then we're okay, right? So let me just write out here when this is the case. The inequality, we'll say when this is the case. Let's just keep it short. I don't want to get to too many things. Things are going wonderful. Going wonderful. Let's see here. n1, n2. We have, now I'm just going to sum over the two inequalities. We had one for F, one for G. Now I'm going to write their right-hand sides on this side here. So that was C1 times H of n on the first inequality, one relating to F of n. The second one involved G of n, so that's C2 times H of n. And now if you just look at this carefully, you'd have C1 times this, C2 times this, but this is the same among both of them, so I'm just going to factor that. So now I'm just going to have it where it's C1 plus C2 times H of n. But if you look very carefully at this, it's F of n plus G of n is less than or equal to C1 times C1 plus C2 together times H of n. But this looks just like what we wanted to prove, right? You could just make this C, and you just make this n0, and you're done, right? But let me state that. By selecting constants, C is equal to C1 plus C2, and n0 is equal to the max of n1, n2. Let me just, n1 is sort of melting into n2. I'm going to fix that. There we go. n2. Then we have that F of n plus G of n is less than or equal to C times H of n. And this holds for all n greater or equal to n0. So now I just need to pull up the definition of big O, and then we're done this proof. Isn't that nice? So now I have the two constants. Therefore, by the definition of big O, we know that F plus G is big O of H. And that completes the proof. Isn't that nice? So just to be clear, so what this is saying is that if you know that one complexity function is big O of one complexity function, and the other one is big O of the same complexity function, when you add the two, it should end up being that same one. So just like I had here, where I had F and G together, where I sum them together, they belong in the same bucket as if I put them separately. They should belong in the same one if they both belong to big O of H.